last form of radiation we're discussing is gamma decay. Gamma radiation can only be stopped by a few inches of lead. And gamma radiation is different from the others in that it is not a particle that is emitted, it is a form of electromagnetic radiation. And it's electromagnetic radiation with very high frequency and very high energy, and it can be very, very dangerous, gamma radiation. Gamma decays happen most often after an alpha or beta decay. This happens because the nucleus has just been through a lot, spitting out other subatomic particles, changing from a different element and all that. The nucleus is basically all jiggled up and needs to release some energy somehow. An easy way to do this is let off a gamma burst. Because we are releasing energy, not particles, the A and the Z values stay the same. So gamma decay equations are pretty darn simple. If you take argon 40 that was produced in the last example, in excited state, it releases a gamma radiation. You simply write it like this. Argon 40 produces a gamma ray, which kind of looks like a Y, plus lowercase r, argon 40, and that's it. That's how you write a gamma ray equation. So it's pretty straightforward, and I think that's all we need to say about gamma radiation. Then we can go through a decay series. Anytime a nucleus decays, the daughter nucleus itself may be still unstable. So it will decay into something, and then if it's still unstable, it decays further. In this case, the daughter nucleus is now the parent nucleus and will go through another decay. This is called the decay series. Write a decay series for thorium-226 decaying to astatine-214. Without looking stuff up, we have no way of being certain which decays will happen, but we can make guesses and see if we end up in the right spot. We will leave out gamma decays here since they do not change the number of nucleons. So we're starting with thorium-226. And we know thorium has an atomic number of 90. And we're trying to get to astatine-214, which has an atomic number of 85. So that's where we're trying to get. So you could do this in a number of ways. You could say that it goes through 2 alpha decays and then a beta negative decay. Or you could say it goes through a beta negative decay and 2 alpha decays, or an alpha, a beta negative, and then an alpha. And really, unless there's some indication in the question which way to go, you could just do it anyway. So let's say that we first go through we got a 90 and we need to get to an 85. Let's change that 90 to a negative number. So let's say that we go through a no, let's not. Let's actually go through the alphas first, just because those are the ones I have written out here. So if this goes through alpha decay, 2, 4, it then becomes, and I don't have my periodic table here, so I have to do the one that I've got written here. So it's going to become radon. Was that radium? 88. 2, 2, 2. All right, so now we're at an 85. Let's take that 85, or 88, sorry, 88. Let's take that 88. And then we'll put in our beta decay. And as I said, you could do this in any order as long as you end up with an 85. You could have done the beta negative decay first. I just don't have the periodic table right now, so I'm a little out of my element here. Oh, another great element pun. Oh, gosh. Killing it. So now let's do our beta negative decay, and that is going to turn this into, now the other thing you could have done here, was a beta positive. So I should have said beta positive, not beta negative. If we do a beta negative here, this is going to get it to an odd number. And we want an odd number there. So I'm going to do a beta negative decay here to get it to an odd number, and that turns it into actinium. And from this point, I don't think I need to do the rest. You can see at this point, I could do now two alpha decays, and I will eventually get to an 85 right there. So again, the moral of this example is that you can use a variety of methods. The first method I said was a beta positive. I should have said beta positive, not beta negative. A beta positive and two alphas. You could have done that. Or in this example, we're going to end up doing 3 alpha decays and a beta negative. And you can do them in any order you want. They will, if we do this experimentally, then scientists will probably see what elements tend to do. Do they tend to do two alphas and then a beta positive, or 2 alphas and a beta negative and another alpha decay? So there will be a tendency for elements to probably do one or the other. Okay, and that ends that lesson. No, it doesn't. There's more here. There's radiation risks. This is something you can you just read by yourself. You're not going to be tested on this. And you're not going to be tested on this terminology here, rad, gray, sieverts. They're just ways of measuring radiation. But this is what you probably should know, is right down here that alpha particles, this is actually stuff you definitely do need to know. Alpha particle has a high ionization rate but cannot easily penetrate matter. So a layer of clothing will protect you from an alpha particle, but it can ionize. In other words, it can take the electrons out of particles. Alpha radiation is really only a danger if you either breathe it in or swallow a source of alpha radiation. Beta does not ionize easily, but it can penetrate matter more easily, traveling about 0.5 meter through the air and about 1 centimeter into the body. So beta radiation can be more dangerous, and gamma radiation can easily penetrate your body. It's high frequency EMR. It doesn't ionize as much, but it causes the most amount of damage to a person. Okay, and that's it. I think we're done with decay. Yep, the end of decay. We'll move on to the next lesson.